At this point, we are going to look at some predefined random variables, which we encounter quite frequently to represent certain quantities that appear in real life. The first one and the simplest one is the Bernoulli random variable with the parameter p. Sometimes this is also called the Bernoulli trial, and this represents a two-outcome random experiment, which we name either success or failure. And the success outcome is mapped to the real value 1, and failure is mapped to 0, and p, this parameter here, is the success probability. So the probability that the random variable equals 1 is p. The probability that it equals 0 is 1 minus p, and obviously it is 0 otherwise. So depending on the value of p, let's say p is greater than 1/2, and this is p, this is 1 minus p. This is the PMF of the Bernoulli trial. Okay, so p here is a parameter between obviously 0 and 1. How do you find the expected value of this? 1 minus p times the outcome 0, because 1 minus p is the probability assigned to outcome 0, plus p times 1, you get p, the mean value of expected value, the expected value of the Bernoulli trial. And what about the variance? You compute the variance by, again, computing the average of, if you remember, k minus the mean squared. So 1 minus p is the probability assigned to which outcome 0. And since the mean is somewhere here, p, 0 minus p squared times 1 minus p plus p, probability assigned to outcome 1, 1 minus p squared. So 1 is the outcome minus p, p here is the mean. And if you arrange this, you get, this is p squared, this is 1 minus p, plus p times 1 minus p squared. If you actually arrange this, you get p times 1 minus p as the variance of the Bernoulli p trial. When do we use this random variable in real life? To model, for instance, a coin toss is the simplest example. For instance, 6 on a die or not. Obviously here you are, since this is a two-outcome random experiment, you have to actually classify your possible outcomes into two groups, 6 or not. Or for instance here, 1, 2, 3, 4, 5 represents failure, 6 represents success. That's our naming convention. It doesn't necessarily relate to real success or real failure. Or for instance, to represent whether a baby is a boy or a girl, because it's a two-outcome experiment, you can use the Bernoulli trial to represent this. Or whether it rains on a day or not. If it rains, outcome 1. If it doesn't, outcome 0. Or pass, fail in a course. Or more practically for an engineer, object detection on radar, right? An object exists or an object doesn't exist, for instance. Another important random variable is the binomial random variable, and it has two parameters, n and p. And this random variable represents the number of successes in n independent Bernoulli p trials. So you successively perform n Bernoulli p trials that are independent. And therefore, the sample space is going to be numbers from 0 up to n, because the number of successes can be 0, can be 1, 2, 3, etc., up to n. You can't have more than n successes out of n, obviously. So for any specific outcome sequence, theta 1 up to theta n, where each theta is either a success or a failure, the probability of any specific sequence is p to the power k times 1 minus p to the power n minus k, where k represents the number of successes, obviously. But of course, we are not interested in the order, we are just interested in the number of successes. Therefore, out of n, to have k successes, there are n choose k possible orderings that will give me k successes. So if I multiply this with this probability, I get n choose k times p to the power k times 1 minus p to the power n minus k, where k is between 0 and n, is the PMF function of the binomial random variable. Now, as we have seen, the sum of all probabilities of a PMF should add up to 1, and you can verify this on this PMF by adding this from k equals 0 to n, and by the binomial theorem, this gives 1 as expected. And what about the moments of the binomial random variable? The expected value, k multiplied by this probability, you add them from k equals 0 up to n. This gives you n times p. I'm not deriving this. It's not a difficult sum to derive, but it will take some time. So I'm skipping the derivation. You can find it on probability books, or you can find it online if you like. Similarly, you can compute the second moment by using k squared in the sum, and this is the PMF. Add them up, you get this expression, and then from this, if you subtract the square of the mean, which is NP, you get the variance, because variance is equal to second moment, if you remember, minus square of the mean. And the variance turns out to be n times p times 1 minus p. And the next random variable we will talk about is the geometric random variable. This is also related to Bernoulli trials, and it represents the number of fails in a series of independent Bernoulli P trials observed before the first success. So for instance, you are repeatedly tossing a coin until you see heads, and you are counting the number of tails in this random experiment. So it could be 0 if you toss a heads in the first trial, or it could be 1, like tails, heads. It could be 2, tails, tails, heads. It could be 3, tails, 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 heads. So it goes to infinity. So the support is natural numbers. And the PMF is simply 1 minus p to the power k times p, because this is the probability of the first k fails, and this is the final success. And the expected value can be computed by this infinite sum, k times the PMF here. If you compute this, again, I'm skipping the derivation. It's not that difficult. It turns out to be 1 minus p divided by p. Similarly, compute the second moment by putting k squared here. And this turns out to be this expression after some manipulations. And I'm skipping the details. And you can obtain the variance by subtracting the square of the mean, this one, from the second moment, which gives us 1 minus p divided by p squared. And as I said, some examples, number of coin tosses before first heads, or number of die throws before I get a 6. Okay, so for instance, what is the distribution of the number of die throws before I get 1? It's a geometric distribution with a parameter 1 over 6. There is a second version of geometric random variable, and it counts the final trial, which is a success. So the number of trials rather than the number of fails is defined as the number of trials before the first success. So the final success is included, which means simply this is if this is x, then the second version is y equals x plus 1. That's it. You just add the final trial. So simply the support is now not the set of natural numbers, because it cannot be 0. It can be at least 1, because you need the first trial. And therefore, it's 1 minus p to the power k minus 1 rather than k times p. And the support is 1, 2, 3, etc. And the mean value is actually this plus 1, because if you remember, when you apply a linear function to a random variable, the expected value also experiences the same function. And the variance does not change. Why? Because if you just shift a distribution, let's say the spread of the distribution doesn't change, so a variance is not affected by shifts. Therefore, the variance of x here and the variance of y are equal and to this quantity. Okay, so the final random variable we are going to talk about is the Poisson random variable with a parameter of lambda. Now, this is a curious random variable, and it represents the number of occurrences of a completely random event within a given time interval. So what does this mean, completely random? First of all, we know the mean number of events in this given time interval to be lambda. This is a parameter given to us. Somebody says that, okay, so let's say within an hour, lambda of these events occur on the average. We know this. And on top of that, if we say that those events occur in a completely random fashion, and then this means you can apply a Poisson random variable to this quantity. So what does this mean? We start by actually discretizing the given time interval into n slots. What we are going to do is, well, you see, when we say completely random event, what we mean is each of these slots, okay, they are independent of the others. That's what we mean by completely random. And they have the same probability of hosting an event occurrence. And we take n to infinity, which means it's a very large number, so large that each slot is so small, n is so large, which means every slot is so small. That means the probability of 2 or more events in a slot is negligible. So in every slot here, either 0 events or just a single event. So what does this mean? This means that every slot is effectively a Bernoulli trial. What is the parameter of the Bernoulli trial? Lambda divided by n, because I know that in total, I expect a total of lambda events in this interval. So in each slot, it should be lambda divided by n. So in total, it should make lambda. Therefore, this means I have n slots here. Each of them is a Bernoulli trial. Each of them is independent. Each of them has a parameter lambda over n. Therefore, the total number of events in this interval has a binomial distribution, because if you remember, binomial distribution is equal to the sum of n independent Bernoulli trials. So we are going to base our derivation on this, and essentially Poisson random variable is the limiting case of the binomial random variable as n goes to infinity, the number of Bernoulli trials, p, the parameter of the Bernoulli trial goes to 0, but their product, n times p, equals to lambda, is constant. So this limit, n choose k, p to k, 1 minus p to n minus k, I'm not again going to go into the details of the derivation, but it turns out to be lambda to the power k divided by k factorial times e to the power minus lambda, and the support is natural numbers, 0 event or 1 event or 2 event, etc. The expected value, the second moment and the variance, again, we apply the same formulas to obtain. Essentially, expectation is lambda, and variance turns out to be equal to lambda also. And in real life, when do we use Poisson distribution? It's usually used to model random occurrences of events, such as the number of radioactive decays from a radioactive sample within a certain interval, for instance, the number of calls arriving at the call center within an hour, the number of malfunctions of a machine in a year, etc. Okay, so such events can be modeled using a Poisson random variable.